at these. So we're looking at our single replacements. We're going to go through and try and balance these two equations. We'll do the first one for you and then have you guys go through and do the second one. We'll spend a couple minutes doing that. So solid copper metal, when we go through to interpret, don't try and do the whole thing at once. Break it into smaller sections. So we have solid copper metal, which means I'm looking at the symbol for copper. It says it's a solid. I'll specify the phase. That's all we would write as far as that goes. Is mixed. Well, that means plus sign. Okay? Or technically, I guess, is mixed with. And then aqueous aluminum nitrate. So aluminum nitrate, so now I don't care about anything else, it's just what aluminum nitrate is. The symbol for aluminum is Al, the symbol for nitrate is NO3. Okay, I could even go through and specify the phase, which I'm going to need to give myself a little bit more space on this. Put in the AQ. Okay, last part of this, to produce, there's our reaction arrow. So we would be expected to predict the products, which I'm going to have to do on a second line. Sorry about that. I don't like doing that, but it's the way it's going to have to work here. Before we move into predicting the products, let's make sure that what we've translated from the question is valid. So it's balancing our formula. Is our formula for solid copper metal correct? Yeah. Is our formula for aluminum nitrate correct? Okay, why is it not correct? Aluminum is a +3. How do you know it's a +3? That's one that you should have memorized. You could derive that one, but it probably makes more sense just to have that one memorized. The nitrate is -1. How do you know that? You had that memorized. Does our charge balance? No. So we have to balance our charge first. How do we balance the charge? We need 3 nitrates. If I just put a 3 here, okay, it's not that that's necessarily wrong. I know what that 3 means, but if I wrote that on an exam, would you know what that 3 means? No, that looks like it could be 33 oxygens. Okay, so what we want to do is include the parentheses to specify that. The way we came up with that was purely nomenclature. That is chapter 6. A lot of what you're going to be doing is going back and using your nomenclature skills to balance out each of these individual formulas. Okay, you are expected to have that relatively mastered. Okay, it's unfortunate, but that's the way it's going to work. Is that a question?
Yeah, with the aqueous, do we have to put parentheses around the whole thing?
No. So, no. Our phase is always implied for the entire thing before it. It's an interesting question, but we don't have to worry about that. Is our formula now correct for our aluminum nitrate? Yeah, so now what we can do is move into our products. What type of reaction are we doing? Single replacement. What happens in a single replacement reaction? We need to swap our metals. Okay, so if we write this out, we're going to end up now with aluminum as the, come on, pen. Aluminum as our solid, plus now copper with nitrate. You'll notice I am not including the parentheses in the 3 at this point. Oh, crap. I picked the wrong one. Okay, we have to look at it. The next one is one you'd be expected to predict the products on. Okay, I did a better job on picking one for the next one. Okay, how would we decide that our formula is balanced? If we go back and look at our aluminum solid, is that formula balanced? Yeah, aluminum solid is aluminum solid. That's balanced. How about our copper nitrate? You should be getting a mixture of yeses and nos. Why should we get a mixture of yeses and nos? What is the charge on copper? It's one that has to be defined or given to you. Okay? So I swapped the two reactions that I should have done. Okay? In this case, we don't know if copper is supposed to be +1 or +2. If you don't know that, can you properly balance that formula? No. Okay? Just to make things interesting, let's assume it's copper +2. Okay, what's our charge on the nitrate? Okay, is our formula balanced? What do we have to do? We need 2 nitrates. In the process of balancing that formula, do I care how much aluminum we started with? Do I care how many nitrates I started with? No. Both of those questions are irrelevant. You must balance the formula. The formula requires looking at the charge. Once you've got your formulas balanced, then we can go back and start to see and compare left and right on the reaction. Okay? With balancing this one, because I didn't put it in one line, I'm going to try and do this as quickly as I can in my head. We'd go through and evaluate copper and copper. Are those balanced? Yes. Aluminum and aluminum? Yes. Nitrate? No. We have 3 nitrates as a reactant and 2 as a product. What's a common multiplier between 3 and 2? How do I make 3 equal to 6? Multiply by 2. How do I make 2 equal to 6? Multiply by 3. We've now changed a number. As soon as we've changed a number, that means we go back through and check our work. How many coppers? 1 versus 3. Is our copper balanced? How do we fix it? 3 in front of our copper. Okay. Our aluminum's balanced. 2 versus 1. How do we fix it? 2 in front. Check your nitrates. They're 6. What do we do now? Check it all again. Okay. The next question with this is then and determine if a reaction will occur or not. Okay. When I go through and process, I like to draw out each of the individual reactions first, okay, and then evaluate. And what I go through and do is circle my ionic state for each of my metals. So in one case, I'm looking at the aluminum as an ion. And in the other case, I'm looking at copper, as an ion, as an ion. Okay. The copper as an ion is a reactant or a product? Is it on the left side of the reaction or the right side? I know it's a product, and our aluminum is a reactant. So now to determine if the reaction occurs, we will go to our activity series, and we want to compare aluminum and copper. So we've got aluminum here and copper here. Which is higher on the activity series? Aluminum. What was my interpretation of the activity series? The higher on the activity series, the more it wants to be an ion. So aluminum wants to be an ion. So now we go back to our reaction. Where is aluminum an ion? On the reactant side of the equation. Aluminum starts as a reactant. There's a sneeze really bubbling up. What are you guys talking about? That hurts. Where is aluminum an ion? On the reactant side or the product side? On the reactant side. Aluminum starts as an ion and it wants to stay an ion. Does the reaction progress forwards? No. So our end conclusion for that is that we get no reaction. Okay? Questions about that? Okay, I'm going to give you 2 minutes to work on that next problem. It's been started for you, though not finished. Okay? It's missing some very key important pieces. Okay? I will tell you that the left side of the equation is fine. Assume copper is in the +2 state. I've balanced that side. I have not balanced the products. Okay? So make sure your product formulas are correct before you go through and start to balance the equation. Okay, so if we go through it again, remember I said the left side of that equation is balanced, which means our copper has what charge? It is defined as a +2. I told you that side is okay. I told you the right side has problems. Where are the problems on our right side of the equation? Aluminum carries a +3 charge. Sulfate carries a -2. Is that formula balanced? No. So we're going to have to fix that. How do we fix that? Oh man, this is really tight. Try to give more space. We'll have 2 aluminums and 3 sulfates. Okay. Now that our formulas are balanced, now we can go through and balance the equation. How do we balance the equation? Okay, you guys are jumping steps, and I know some people don't like doing that yet, so let's avoid that. Aluminum is 1 on our reactant, and we have 2 as a product. How do we fix that? We need to make the 1 equal to a 2, so we'll put a 2 in front. We can move to copper next. How many coppers do we have? We have 1 and 1. So far, so good. And then we've got our sulfates. How many do we have on each side? We have 1 and 3. Is that balanced? Nope. What do we have to do? So put a 3 in front of our copper. Now we've got our 3 sulfates. What do we do now? Go through and check. Aluminum and aluminum. What are our numbers? 2 and 2. It's balanced. How about copper? We're now at 3 and 1. Is that balanced? What do we have to do? We have to make that 1 a 3. Sulfates. Are sulfates balanced? Okay, we still have 3 and 3. What do we do now? Go back through and check your balancing. What do you do then? Check your balancing again. And now we can go through and decide if the reaction has occurred or not. Okay? To go through and do this, one of your classmates has a slightly different spin on it than I've been going through with it. So Zoe, would you like to go ahead and explain that?
So in our lab group, we kind of thought of it as like your aqueous solution or your ion is a bus seat. And so let's say you paid $5 to sit in your bus seat. Oh.
Go ahead.
Okay, so you paid $5 to sit in your bus seat. And somebody else comes up to you and they say, hey, I'll give you $2 for your bus seat. You're going to stay where you are because it makes more sense for you to sit there because you paid more. But if somebody comes up and they're like, hey, I'll give you $20 for your bus seat, you're going to be like, oh, yeah, sure, that made me a profit. So you're going to move. So if it has more activity or more money, then it's going to get the seat, basically.
Okay. So if we go through and evaluate our seat is being paired up with your sulfate ion. So our sulfate is that seat. Okay. Which of those two metals, copper or aluminum, has more money? We go back and look at our ranking. We've got aluminum and we've got copper. Which one has more money? The aluminum. Which means copper says, heck, I'll make a profit, have my seat. What does that mean? Aluminum is favored to get the seat. Where does aluminum have a seat? Reactant or product? Product. What happens? This reaction occurs. Okay? So it's just a slightly different spin on what we've talked about. Okay? Hopefully that helps you out. If it doesn't, either keep talking with me, you can talk to Zoe after class, talk to other people, try and come up with some way that you start to interpret and understand that activity series. Remember, your activity series will always be given to you on the test. It will have some modified version of it, but it will be given. Do not expect you to memorize that. Okay. So what we're going to look at now is ultimately Chapter 17. with our single replacement reactions, one of the things that's happening is we're transferring electrons from one atom to another. Okay? So what we want to go through and do is further refine that transfer of electrons. Okay? So what we'll have to do is identify the oxidation states of each of the atoms. Oxidation states are very, very similar to charge. Okay? Charge applies to a unit. Okay? That unit could be a molecule, it could be an atom, it could be a compound, it could be a million different things. Okay? The oxidation state only applies to an atom. Okay? So they're slightly different as far as their interpretation. Sometimes the charge could apply to an atom, in which case the oxidation state is the charge. Other times it's not. There are some rules that you absolutely have to have memorized when trying to determine your oxidation states. Okay? For me personally, those absolute memorization rules are going to be your A, B, and C. Everything else you can effectively derive. Well, sorry. We need A, B, and C, and we need Rule 4. Okay? All other rules can be derived by using rules A, B, C, and rule number 4. Rule number 4 is what's allowing us to determine the relationship between our charge and our oxidation state. Okay? So if we add up the oxidation states of every single atom within an individual unit, that must equal the charge on that unit. Where do you find the charge of an individual unit? Upper right-hand corner. So you are always given the charge. Okay? So you can apply that information back to then adding up all of your oxidation states and determining what your either individual oxidation states are, or potentially even figure out what your charge might be. Okay? What is the charge? Man, it's coming back. What is the charge on each of those individual molecules within that equation? All of them have 0 charge. Why? The upper right-hand corner of every single one of those molecules or units has nothing written there, which means 0 charge. Can we say the same for the oxidation state for every single one of those atoms? No. To determine the oxidation state, we would have to go through and apply these rules through each of these individual issues or units. Okay? We could derive the charge, our oxidation state on that very first one, or if you happen to expand your memory a little bit, rule number 1 was anything in its elemental state has an oxidation state of 0. Okay? We could just as easily derive that very, very quickly. Okay? So let's take a look at that one real quickly before we go on to other examples. If we say we do not know the oxidation state of calcium, that is going to be X. How many calciums are in calcium solid? There is only 1. Okay? Plus the number of any other atom. How many other atoms are there? There's no other atoms within that unit. Times their oxidation state. Oh, I don't know what their oxidation state is. Does it matter? No. 0 times anything is 0. So that term disappears. This has to equal what? Give me in words. Don't give me the number yet. It must equal the charge. What is the charge for that unit? How do we know it's 0? Charge has nothing to do with elemental state. Charge is always specified in your formula. Okay, we know it's 0 because when we look at our formula, what is written in the upper right-hand corner? Nothing. What is the symbol for nothing? 0. That's our charge. So now we solve the equation. 1 times x equals 0. What is x? 0. What's our oxidation state for calcium? 0. There's rule number 1. Okay? So rule number 4 allows us to determine what that is. Okay, we could do the same thing with rule number 2. You get the same general process. So where we ended, I'm pretty sure we ended with this slide, right? Okay. We could go through and look at 4 possible examples and separate them out as charge and oxidation state. Remember, charge is the number written in your upper right-hand corner for every single formula. Okay. We could adjust that to unit. It's kind of up to you how you want to define it. I'm looking at that very first term, Cu, as a formula. That formula also happens to be a single atom. Okay? Kind of irrelevant, but that's all it really is. It just happens to be a single atom formula. What is the charge for that atom or that formula? How do you know it's 0? Upper right-hand corner, there is nothing written, so it is 0. What happens with the next one? Our charge, upper right-hand corner, +2. What's the charge for the next one? -1, upper right-hand corner. We see a negative. Last one, -2. Okay? So your charge is almost always given to you with an individual formula. The few cases where it's not given to you, you are expected to have it memorized. So for nitrate and sulfate, those ones you should be expected, or you are expected to have memorized. So if I asked you for the charge on the sulfate ion, you would convert the word sulfate into the formula SO4. Since it's the sulfate ion, you also need to know that the SO4 ion has a -2 charge. Okay? So you've already spent some time to memorize this. Depending on the question asked, it might be given to you, or you might have to have it already memorized. Okay? So we've got all of our charges specified in that upper right-hand corner. Okay? What about the oxidation state? Okay, well, our formula for oxidation state, it's the number of that element times its oxidation state plus the number of the next element in that formula times its oxidation state plus the number of the next element times its oxidation state, so on and so forth. When we add all of those up, that's what gives us our overall charge. Where do we find that charge? Upper right-hand corner. Okay, so let's go through and take a look at the second one, because we've effectively already done copper by itself. So let's take a look at copper +2, our copper ion. How many coppers are in that formula? There is 1 copper. What is its oxidation state? This is where it's getting a bit tricky. The oxidation state must be defined, okay? Which means, technically, you do not know what it is yet. It is X. How many of the next element are there? 0. So we don't have to worry about it anymore. That totaled has to equal. Why does it equal +2? That is the overall charge on our molecule, upper right-hand corner. What does X equal? X equals, and I know everybody's saying 2. I'm not really happy with that. Really what I want to hear is +2 or +2. Okay? The reason why I want you to go through this extra work ultimately, or in my opinion, becomes more apparent when we move to the next 2 possibilities. Let's determine the oxidation states for nitrate. Okay. Oxidation state applies to what? Single atoms. So what we have to go through and do is solve for our oxidation state. Since nitrogen is the first one, we might as well attempt to deal with that first. So how many nitrogens are there? There's only 1. Times its oxidation state, X, plus how many oxygens are there? What's the oxidation state? We'll stick with Y for the moment. For those of you saying -2, you are correct. We'll come back to that in a second. How many other atoms are there? None, so we don't have to worry about it anymore. This has to equal what? Negative 1. We have one equation and two unknowns. We cannot solve for those yet, so we need some more information. What's that more information? Rule 3A. Rule 3A said that oxygen had what oxidation state? Negative 2. Y equals negative 2 from Rule 3A on my list. What can we do now? 1 times x is x. 3 times negative 2. What does x equal? X equals negative 1 plus 6 to both sides, which then equals plus 5, or positive 5. Okay? We have now determined the oxidation state. Well, 1 second. We said x is plus 5. What did x mean? The oxidation state on nitrogen. We could now go back and say our nitrogen has an oxidation state of plus 5. Okay? Should we do sulfate? I heard one yes. It's good enough. What's our oxidation states for sulfate? We're going to go through the exact same process. How many sulfurs are there? What's the charge on sulfur? Or sorry, oxidation state on sulfur? Plus, what's the next atom? There are 4 oxygens. What's the oxidation state of oxygen? Negative 2. Interesting. You decided to skip a step. Is that a step that's valid to skip? Yes, as long as you absolutely know. If you don't absolutely know, put it down as Y, and then you have to remember Rule 3A. Okay? How many other atoms are there? None. So we can now say equals. Why is it negative 2? That is the overall charge on that molecule. Simplify. X minus 8 equals negative 2. Add 8 to both sides. We get x equals positive 6. What did we say x was? Don't tell me plus 6. The oxidation state on sulfur. Okay? In theory, with enough practice, you should be able to do this algebra in your head and get your answers, your oxidation states very, very quickly and efficiently. If you have to break it down into each of the individual steps, absolutely go ahead and do that. Just realize it is going to take you more time. You're going to want to spend more time practicing so that you can internalize that so you can get through more problems on the test. Yes? Halides. What are your halides? Your halides are group 17. What's the name for your group 17 elements? Halogens. How did we get halides? What does the IDE ending imply? The ion. Okay. What is the ionic state for your halogens? They would then be known as the halides. Okay, so all we've done was change the suffix around to make it charged. Okay? So what are we going to do with this information once we now have it? Well, we're going to have to apply it back to individual reactions. Okay? I'm going to trust that you guys can go through and determine the oxidation states for every atom within that equation. Okay? And I'll leave you to figure that out on your own and verify that I did balance it right. Doesn't mean I did, but hopefully I did. Okay? So we can look at our reactant iodines and we can look at our product iodines. Notice anything different about the oxidation state? Reactant iodine versus product iodine. Do we notice anything different about the oxidation states? Yeah, they're different. Okay? What happened? So one's in its elemental state, one is charged. Okay? Interesting observation. What charge would we expect for iodine? -1. What's our oxidation state? +5. Okay, your oxidation state is not necessarily the charge. You have to determine the oxidation state. It must be something calculated. Okay? So our next issue is what happened to go from iodine plus 5 to iodine 0. Electrons were transferred. How do I go from a plus 5 to a 0? We're becoming more negative. How do we become more negative? We gain electrons. We had to add electrons to it. So if we look at what happened to the iodine element, or the iodine atom in the process of this reaction, we can say that it gained electrons. So that's our summary on the end, what happened to it. We take a look at our oxygen, reactant versus product. Is there a difference in the charge? No. Or sorry, the difference in the oxidation state. No. -2 and -2. So what occurred to the oxygen? Nothing. Nothing changed about our oxygen. What happened to our carbon? We went from a +2 to a +4. How can we become more positive? By losing electrons. Okay? So what we've now got is some extra definitions here, or some extra words. We could go through and for every reaction where we see an exchange of electrons, say that that atom gained electrons, or that atom lost electrons. That's a bit tedious. Okay? So what we've done, instead of saying gained electrons, being lazy, is we came up with a new term to represent the gain of electrons. And we came up with a new term to represent the loss of electrons. What were those terms? Reduction and oxidation. Okay? So what we're now looking at is defining how our oxidation states change. Those changing in oxidation states, we now apply a new reaction idea to. Okay? So we defined the loss of electrons as oxidation, and we can define the gain of electrons as reduction. The neat little mnemonic device that comes along with that is Leo says GER. What is Leo? Fair enough, that's not what I meant. Leo is, what is our Greek term for a lion? I only know of two. The other one that's commonly out there is oxidation is loss of electrons, reduction is gain of electrons, or oil rig. I can't remember oil rig. I think it's silly. Okay? That said, Leo says GER isn't exactly not silly, but whichever one works for you is what you'll need to memorize. You need to be able to decide what's happened across the reaction, so you'll have to determine your oxidation states. When you see an oxidation state has changed, you can then define it as an oxidation reaction or a reduction reaction. When we initially talked about this, the title of this chapter was Oxidation and Reduction. And then I went through and said it's typically referred to as redox. Why is it always combined? Why does something have to lose and something have to gain? Why does that have to happen? Doesn't even have to do with conservation of energy. Let's see. Is this next slide going to do it for me? No. Let's say I look at sodium in its elemental state, and I take that to sodium ion. What happened? It had to lose an electron. What does that lose mean? Lose means that our electron is a product. Okay? The mathematical symbol of a minus in chemistry means product. So what we would do is put plus an electron. Is this equation balanced? How many sodiums do I have? 1 and 1. We could now balance our charge. What's the charge on our left-hand side of the equation? 0. What's the charge on our right-hand side? What's the charge on our sodium? What's the charge on our electron? What's our overall charge on the product side? 0. Is this reaction balanced? What type of reaction occurred? We lost electrons. We're looking at an oxidation reaction. So here's the question again. This is a balanced reaction that shows exactly what happens to sodium. Will this ever happen? No. For this reaction to occur, a reduction reaction must also occur. It has to. Why? Why can it? What's that?
The electron's got to go somewhere.
It's going into the solution. It's going out as a product. We haven't created or destroyed any matter. Everything is still there. And it's still balanced, so you can't argue the complete. What is the stability of an electron? It is ridiculously unstable. We will never find an electron floating off on its own, which means for this reaction to occur, there has to be some place for that sodium atom to give an electron to. It cannot just give it off into free space. Okay? So when we look at our redox reactions, we always refer to them as redox, because if I find a reduction, what else is happening? Oxidation. If I find an oxidation reaction, what else must be happening? Reduction. They must be partnered. Okay? And that's all because our electrons are incredibly unstable. They will not sit on their own. Okay? They must be stabilized by something else picking them up. Okay? So that's why we always tie these reactions to each other. Okay? Any questions about that actually before I keep flipping to that? Okay. So what you need to go through and do again for your steps, identify oxidation states on both the reactants and the products. If your oxidation states change, you're looking at a redox reaction. You get to define, because it's such a fun thing to do, what happened. Was it reduction? Was it oxidation? If you find one element that changed its oxidation state in an equation, what else does that mean? Well, it's not necessarily reduction or oxidation. If there is one element that changed its oxidation state, what does that necessarily imply? There must be another element changing its oxidation state. Okay? Both. We have to have two changing their oxidation states. If we go back and look at the equation written up at the top, what happened? Iodine gained electrons. Where did it get those electrons from? Carbon losing them. Okay? So if you find an element that's changed its oxidation state, there is another one in that equation. You have to find it. Okay? What happens if you don't find it? What does that mean? You made a mistake somewhere. Okay? So go back and check all of your work to determine what happened with your oxidation states. Okay? Questions about keeping these straight? Okay? So this is ultimately our chemistry. We brought in a little bit of English to define things. And now, just because the English majors got involved, I'm going to blame English majors on this one. Okay? We add this new word. We're now looking at an oxidizing agent, or an oxidant, and a reducing agent, also known as a reductant. What happens to an oxidizing agent? An oxidizing agent causes something else to be oxidized. Okay? For something to be oxidized, what happens to it? What happens if something is oxidized? Loses electrons. If my agent causes something else to be oxidized, what had to happen to my agent? It had to be reduced. Remember, they're partners. If we've got an oxidation, we have a reduction. So if I have an oxidizing agent, that means that species was reduced because it caused something else to be oxidized. Okay? How do you know that? It comes back to that ing. So like I said, it's all about English majors. Okay? So if you know any, you can yell at them. That ing and that ant end of this are what's now changing our perspective on it. Okay? What we're concerned about is what that species is doing to something else. So if it's a reducing agent, what did it do to something else? It caused that something else to be reduced, which means that something else gained electrons. What happened to the agent that did it? It had to lose electrons or be oxidized. Okay? It's very confusing. It's difficult to keep those straight. You'll see this a lot more in future chemistry classes, so I probably won't test you too heavily on this. You might see one question looking at your agents or ants. Okay? Questions about those? Okay. Ultimately, it's just a definition. You have to have that definition memorized. Yes?
So if we go back to the last slide with that reaction there?
Sure, we'll go back and then we'll go forwards.
Then, so the I would be the oxidant?
So what happened to iodine? It gained electrons, which means it was
Oxidized.
gaining of electrons is reduction. So iodine was reduced. If we now define it as an agent, it caused something else to be oxidized. So iodine was the oxidizing agent, or we could refer to it as the oxidant. Okay? Nice flips on you, I know. Okay, but that's just what's happening with that. Okay? So let's look at a couple more examples. We'll do the first one together, then I'll make you do probably the second one on your own, and then we'll leave the last one for kind of a homework thing on your own. Okay? So we want to go through and identify. Yes? Yes. Okay? So let's take a look at our first one. We want to identify what changed in the reaction. So let's start with our first symbol. We're looking at tin. What's its oxidation state? We could go through all the math. There is 1 tin. Oxidation state unknown must equal overall charge of +2. What is the oxidation state of tin? +2. What is the oxidation of tin in the product? +4. What changed for tin? Tin had to lose electrons. Oh man, I picked the wrong colors. Loss of electrons, which means it was oxidized. Okay. Before we move on to the agent part, we need to make sure that we have that counter. So let's take a look at our iron. What happened to the iron? Reactant, it was oxidation state +3. Oxidation state of iron in the product. What happened to iron? It had to gain, as I spit on my iPad, gain electrons, which means it was reduced. If we now want to define our agents, if it was oxidized, if we look at tin, if it was oxidized, it was the reductant. I don't know why you guys like the ant version. The reductant or the reducing agent. It is less words. Maybe I'll do that for the next one. So what happened with our iron? It was reduced, so it is the oxidizing agent or our oxidant. Okay? It was a bit mean because I picked the easy one. I'll let you guys go through and do the next one. Let's see. Does it give me all the answers? Okay, it doesn't. All right. So go ahead and work on that next one. Is balancing the reaction. I did not ask you to balance the reaction. I only asked you to determine what was oxidized, what was reduced, oxidizing agent, reducing agent. Any idea why? Look really carefully at this. Is it physically possible for you to balance the oxygens at this point? You can't do it. You do not have the tools to be able to balance the oxygens. Okay? Which is why I didn't ask you to balance the equation. I asked you to figure out what was going on with oxidation and reduction. Okay? That is effectively your 152 material. At this point, you still need to be able to figure out your oxidation states. Oxidation state on copper in the reactant. +2. What happened to it? 0 to +2. It lost electrons, so it's oxidation. I want to make sure I'm color coding right. So copper starts at a 0. It ends with +2. What happened to it? It lost electrons. So if we take a look at our copper, we have a loss of electrons, which means it was oxidized. Before we look at the agent, we have to make sure that it actually caused something else to be reduced. So now we go back through and look at our nitrogen and our oxygen. What's our rule 3A on oxygen? It is always -2, which means don't worry about it. Okay? Don't worry about checking its charge. So let's take a look at the nitrogen. What's the oxidation state of nitrogen and nitrate? We've already looked at this one, so I'll reference you to go back in the slides if you want to look at how to determine that +5. The next one is to look at nitrogen in the product. Since we haven't done that one yet, let's go through and evaluate it. There's 1 nitrogen, unknown oxidation state, plus 2 oxygens. What's the oxidation state of oxygen? -2. What's its overall charge? 0. How do you know it's 0? Upper right-hand corner. Just as a quick question, what if I had written NO3? What's the overall charge on that molecule? 0. Why is it 0? There's nothing in the upper right-hand corner. Do not start to imply information. If you think information was left out, raise your hand and ask. Do not put it in on your own. Okay? If we solve for x, what do we get for x? X equals +4. So we went from a +5 to a +4. What happened? Nitrogen had to gain electrons because it became more negative or closer to the negative values. If it gains electrons, it was reduced. We've now found the partner to our oxidized. So what we can go through and do is say if nitrogen was reduced, it caused the copper to be oxidized. So nitrogen is our oxidant because it caused copper to be oxidized. Our copper was the reductant because it caused nitrogen to be reduced. Okay? So again, we'll address the next issue here. If you went through and tried to balance the overall equation and make sure your electrons balanced out, you would not be able to do it. I do not expect you to be able to do it. Okay? The next equation, I'll let you guys do on your own. If you've got questions about that, you can ask after class. Let's see questions now. Yes? This one is a little bit more complicated to figure it out. You have a complex ion, BiO3, with sodium. What's the charge on sodium? It's always going to be a +1, which then that has nothing to do with oxidation or reduction. All we're trying to do is determine the oxidation states. As soon as we put sodium in a compound, its charge will be +1, which means its oxidation state will be +1. Okay. So this one's a little bit more advanced because of that. But as soon as you put sodium in any group 1 or even group 2 element into a compound, it will immediately become that ionic state. If it's in that ionic state, you can then solve for its oxidation state. Yeah?
How do I know BiO3 is a complex ion and not NaBi?
So that one's a little bit more of a difficult question to answer. Ultimately, what I would go through and do is say sodium has to be a +1, period. So if sodium's +1 and oxygen has what oxidation state? -2. What's the only one you don't know? Talk to me after class. I would argue that you can't. It was Peter?
Never mind.
Okay. All right. Other questions with it? Hi. Oh, come on. So there's your answer to that one. Your answer for that last equation is up there as well. So you can check your work. Oh, there's the quiz. Aha. So we'll go ahead and do the quiz now. Oxidation state for carbon in our reactant. There are 2 carbons with an X oxidation state plus 6 hydrogens with a +1 oxidation state must equals the overall charge, which is 0. How do you know it's 0? Upper right-hand corner. So we get 2x plus 6 equals 0. X equals -3. What is the oxidation state for carbon in the product? Well, there's 1 carbon, X oxidation state, plus 2 oxygens. What's the oxidation state of oxygen? -2. Rule 3A. A. And this equals what overall charge? How do you know it's 0? Upper right-hand corner. We go through and solve. We get X minus 4 equals 0. What is the oxidation state? X equals +4. Did the oxidation state change? Yes. What does that mean? This had to be an example of a redox reaction. So the answer to 3 is yes. Okay? A big tip-off for determining redox reactions. If you see anything in its elemental state, what's its oxidation state? 0. So the oxidation state for oxygen in our reactant is 0. What happens when it becomes a product? -2. So if we see anything in its elemental state and it then changes, must be a redox reaction because that oxidation state had to have changed. That was a nice simple summary there that I'm guessing most of you did not hear because you were talking. That's awesome. Sometimes it's trivial to go through and balance your molecular or your reaction equation based on the information given. Sometimes it's not. If this was the equation you were given, can you balance it? How many zincs are there? Reactant side. 1. How many zincs on the product? How many zincs on the product? 1. How many hydrogens on the reactant? How many hydrogens on the product? Is that balanced? What do we do to fix it? We need a 2 in front of the H+. We go through and check. We check and our numbers check out. So the last step that we would go through and do with our redox, okay, our redox we have to check charges. What's the total charge on the reactant side? What's the charge on zinc? What's the charge on H+? +1. How many H pluses are there? 2. What's our charge? +2. Charge on the product side. What's the charge on H2? 0. Upper right-hand corner. There's nothing written. By definition, it is 0. What is our charge on zinc? +2. +2. Our overall charge is +2. Does our charge balance? Yes. Which means our equation's balanced. Nothing to stress about. We could go through and balance it based on how we've always seen it. But what happens if we switch it up? Okay. What happens in this case? How many tins are our reactant? Tins as a product? How many irons as a reactant? Irons as a product. 1. Sure, it looks like it's balanced based on our standard technique. Go through and check the charge. Charge on the reactant side is +2 and +3 gives us +5. Look at the product. +4 and +2. +6. Does our charge balance? No. What does that mean about our equation? It's not balanced. So we have to come up with a new way to go through and balance it. There are 2 methods that you can use. You can use what the textbook does and then what I will go through and explain probably in the next 30 seconds. Okay? So, textbook's version. What happened to the tin +2? Became tin +4. So what did it do? Lost electrons, which means it was oxidized. How many electrons did it lose? What happened to our iron? Gained electrons. So we're looking at, or rigged, or whoever said oiled. what happened? It gained, or sorry, yeah, no, I did that right. Gained electrons. Oh, I meant to do a loss of electrons on the other one. That's why it looks weird to me. Lost 2 electrons, right? So what the textbook goes through and does is say, take the coefficients of your electrons and now make them the coefficients on your reactants, okay? But swap the order. So it's effectively a version of your crossover rule. So tin lost 2 electrons. So I'm going to put a 2 in front of the iron in both places. Iron lost 1 electron. So I'm going to put a 1 in front of each of the tins. Did it balance? What's our total charge now as a reactant? Total charge as a product. Hey, there it is. Okay, it's now balanced. Do you need the 1? No. Okay. So the 1 is not necessary to include. If I asked for the sum of the coefficients and you didn't include the 1, the habit is you don't add it at all. Okay, so the sum of the coefficients in this case, 2, 4, 6. Okay, one of the other answers would be 4, fishing for that lack of 1. Okay, the other method to go through and do is to split it up into the half reactions. So what I mean by half reactions, look at the reduction, look at the oxidation. Okay, which is effectively what the textbook did. They just jammed it all into one big line as opposed to breaking it down. So we can look at our individual half reactions. Our iron plus 3 went to iron plus 2. Our tin plus 2 went to a tin plus 4. We could balance by adding in our electrons. Remember, an overall reaction does not have electrons produced or consumed. They must balance. They currently do not balance. So what can we do? Run the top reaction twice. If we run the top reaction twice, that means I need 2 electrons, 2 iron plus 3s, and 2 iron plus 2s. So I go through and change those numbers around. Oh, come on. I stepwise this way too much. Okay. Now when I add up the reaction, I get the exact same balancing that we went through and did the other method. My method is a little bit longer, but it shows all the individual steps in the work. It does the exact same thing as what the textbook has shown. Okay? We did run a little bit late on that. We'll finish up chapter 7 on Tuesday and move into chapter 8 and 9. Remember, 8 has been condensed. We're looking at about half of that chapter. And we've definitely pulled some sections out of 9 as well.